All right, here we go. Two more problems, and then you can, do whatever. Wait for classes to start again on Monday. So here we go. We've got a ball weighing 50 newtons, and it's pulled back by a rope to an angle of 20 degrees from the vertical. What is the tension in the pulling rope? So this is probably, I think, our first problem with multiple dimensions. All the other problems we've done so far are, the forces are restricted really just to one direction. So if we're going to solve this problem, we definitely want to draw a proper force diagram. It might be tempting to just draw the forces on the picture, but really I highly recommend that you draw the force diagram so you get all of the angles done correctly. Okay, so clearly the ball is touched by two separate ropes. You have a tension force that's off at the angle, and I think I'll let it be a black color. And then you have the other force, which is pulling off to the left, and that's the tension force that you're actually interested in. So let's just call that F tension, the one we're looking for. And sorry, I didn't label the other one. Let's call this F. Let's just call it F. The force in that rope, it's technically a tension force, but I want to leave it without subscripts, and you'll see why here in a moment. And then we'll have one more force. It's not a contact force. Presumably the Earth is down below the ball here, and so we'd also have an F grav pulling it in the downward direction. It is most definitely worth your time to make sure that you put in your angle in some way correctly here. So I'm just going to extend the vertical axis so I can visually see it, and the horizontal axis so I can visually see it. We can maybe come back up to the picture itself. If I were to draw another vertical line in here that is parallel to the vertical line that's already drawn in here, we can use a little bit of geometry to tell us that alternate interior angles of an intersecting line of two parallel lines would have to be equal. So that means that between the new vertical line that I just drew in and that rope is also the 20-degree angle, which would correspond down here on our force diagram to the 20-degree angle being here. Okay, and I like to put it there, and you'll see why here in a second. So this is our force diagram. Technically, this is all that would be required if all you had to do was find a force diagram. However, we want to be able to sum our forces, which means that it becomes really important that we break this force from that rope from the upper right-hand side into its two components. It might be useful to color coordinate, so that's what I'm going to try to do in this solution. But this force that I just labeled with F has a vertical component, which is right here, and I'll call that Fy since it's in the vertical. And I've colored it blue so that it is in the same color and direction as F grav. And then if you add to that Fy, you would have an F sub x. So when you add Fy to Fx, you get the full force of tension that's pulling to the upper right-hand side of your picture. Okay, and again, I labeled it using the red marker so that it coincides with a horizontal direction. Okay, so we want the F tension, the one that's going off to the left. That's the one that we need to find a value for. So technically, we need to sum our forces twice here. We technically need to sum our forces in the horizontal direction and see if they equal to mass times acceleration. Okay, and then we'll also have to sum them in a y, but I'll write that here in a second. So if we sum our forces in the x direction, taking, right as positive, up as positive, though the up doesn't matter, but just establishing directions. So that means that we would have the F sub x, that thing is pointing to the right and therefore in the positive direction. And then the only other force that is in the horizontal direction is the tension that we're looking for, which is minus that F tension. Okay, if the ball is just being held back, it's not going to be accelerating, so there is no acceleration, and the sum of those two forces needs to be equal to 0, or the Fx equals the F tension. This is a bit of a letdown because we don't know Fx and we don't know Ft, and we need the Ft. Okay, so as with the projectile motions, when one piece fails, you look to the other. So now we want to see if we can't sum our forces in the vertical direction and see if we can't get more information there. So if we're only looking at force vectors that are in the vertical direction, that means we have the Fy. Sorry, those were really bad names in retrospect. That's going up, and so it's positive. And then counteracting that is Fgrav, and that's going down, which is the negative direction. Again, the ball is just being pulled back. It's not accelerating. So the sum of those two forces needs to be equal to 0. And so what this tells us is then that the Fy, that piece of the big F, is equal to Fgrav. Now this has a little bit more promise because we can use this. So we want to do maybe a little bit of trig. If we consider our triangle and we're considering the side that has the Fy in it, because that's what we have right now, then that's the side that's adjacent to the 20-degree angle. So if I look at cosine of 20 degrees, that's going to be my Fy over F. And that might seem not terribly helpful, but it really actually is helpful. And it's helpful because I can do the same treatment for the side that's opposite, right? I could go and talk about the sine of 30 degrees, and that would be equal to like Fx over F, which is nice because then I could say, I could solve for F, and I'd have Fx over sine of 30. So then on this other side, I have, oh, sorry, that's not what I want to solve for. My bad. We want to solve for Fx. If we solve for Fx, that's equal to F sine of theta, sine of 30. And so that would mean that we have F sine of 30 equals Ft. And that's good because if I can solve for F in the horizontal or in the vertical, I could then plug it into the horizontal, right? So if I solve for Fy, I would get Fy equals F cosine of 20. Sorry, I made up 30. I didn't mean to make up 30. My goodness. I just got all excited. 20, those are all 20s. Okay, so with the cosine, so I have F cosine of 20 equals the Fgrav, but I know the Fgrav, it was part of my information. The Fgrav is the weight, which is the 50 newtons. Okay, so this is 50 newtons. So the F force we can quantify as 50. Oh, that did not work at all. It's 50 newtons divided by the cosine of 20. And so now I can take this value and put it into my horizontal. And so we'll have 50 newtons times the sine of 20 divided by cosine of 20 will equal the force that we're looking for. So all this work, okay, plug that into your calculator and you should clarify or double check that you get 18.2 newtons. Whoa. Struggles. Sorry, guys. Okay, so lots of arrows. It gets easier when you do more of them, but you had a picture, you draw a force diagram, you break any vectors that are not going along the x or y direction into their x and y components. You then need to solve or sum your forces in the x direction, sum your forces in the y direction. And apparently it takes 10 minutes to do one problem. Okay, so one more video, then it'll be it.